How can we expect that the parallel program can work if both the compiler and the CPU is allowed to reorder memory accesses? The answer is that machines with a relaxed memory model must have a special instruction for synchronizing memory accesses, meaning that the programmer can insert such instructions when it is required that all previous memory accesses must be completed before the program can continue after this synchronization instruction. So, if we assume that there is a sync instruction, then when the machine comes to that instruction, it waits until it has got all acknowledgements from earlier instructions. And all instructions issued after this, they must wait. I mean, this can happen if we have a superscalar CPU that does speculative execution, for instance. Okay, so let's look at, well, I should first say that we can insert machine instructions in C using this syntax, which is not recommended since it's completely not portable, but it's used for illustration, so to be concrete here. Okay, so what will happen if we do this? And let's assume that both threads have, or CPUs have, a cached copy of variable A. So what happens then is that this write, it will create an invalidation request, and which is sent to memory, and memory will send it to this CPU. Okay, that is going on, and this CPU continues with the next instruction, which happens to be the sync. The CPU must then wait here until the previous memory accesses have completed, meaning that this write has completed. Okay, so it simply waits here until it gets an acknowledgement back that all other copies have been removed. And then it continues. And it will do this write. And, well, we continue to the next slide. So this write will also result in an invalidation request being sent eventually to T2. And T2 will put this in a queue of incoming invalidations. And eventually, okay, so when it receives such an invalidation request, it puts it in a queue and acknowledges it immediately. And this makes the write completion quicker. So T2 is looping here for a different value of f, which currently is 0. And when this invalidation has reached the cache, it will result in a cache miss, and T2 will fetch a new value of f. And that value is this 1, of course, so it will leave the loop. And then it will reach this sync. Okay, so what happens at the sync? It received one invalidation request for A and another for F. And even though they could have been performed in any order, all of them must be performed or applied before T2 can proceed after the sync. Okay? And applied, that means removing the copy of the cache block by invalidating it. So without this sync, there is no ordering for T2, so they could be the wrong. I mean in the wrong order. But with this sync, it must wait until A has been removed from the cache of T2, and then it will, when it has been removed, it will continue and fetch the new value of A. So now it will work. Okay, instead of using this assembly code, we could, for instance, do as in the Linux kernel, and there are macros which result in this suitable machine code for, for that machine, for that computer which we compile on. SMPMB stands for symmetric multiprocessing and memory barrier. Okay, and we shouldn't use this or the assembly code, but instead we can use standardized support in C++ and other languages. Okay, we will come to that for C, the next lecture. But it's the same with a different syntax for C++.